Ladder cable trays are pretty much the backbone of any heavy-duty cable routing. You see them everywhere. But have you ever stopped to ask why? Why are they the industry standard? Well, in this explainer, we're going to peel back the layers and look at the specific, measurable engineering that makes them the go-to choice.
Right, we all know they're the default for big power cables, but what's the real, data-driven story behind that? Because it's not just a habit the industry picked up. Nope, it's actually a series of very deliberate, very smart engineering choices. So, let's start with the most fundamental part, its shape.
See, it all comes down to geometry. The incredible strength of a ladder tray doesn't come from some fancy, complicated feature. It comes from a design principle that is simple, elegant, and, wow, incredibly effective.
The design is just brilliant in how simple it is. You've got these two strong side rails that do all the heavy lifting, handling the main bending forces. Then you have the rungs connecting them. This whole setup works almost exactly like a structural I-beam you'd find in a skyscraper, giving it this amazing load-to-weight ratio. What that means is it can support really heavy cables over long distances without being super heavy itself.
But even with that fantastic basic design, there are some important choices to make. Take the spacing between the rungs, for instance. If you go with a tighter 150mm spacing, you get way more contact points, which is perfect for supporting smaller cables. But the trade-off? The tray is heavier and costs more. On the flip side, you can widen that spacing to 300mm. Now your tray is lighter and cheaper, but you give up some of that support. It's a classic engineering compromise, right?
And what's the result of all that smart geometry? Well, it's the ability to handle some serious distributed loads. We're talking typically between 75 and 200 kilograms per meter. That kind of performance puts these trays firmly into the heavy-duty Class C and D categories, according to the big international standard, IEC 61537.
Okay, so geometry is one half of the equation, but what about the other half? The next huge engineering decision is the material itself. And this is another one of those calculated trade-offs between strength, weight, and the environment it's going into.
And this is a really critical point, especially when you're talking about overhead installations, where every single kilogram counts. Now, steel is strong, and it's common, for sure. But by specifying an aluminum alloy like 6063T5, you can slash the structural dead load. That's just the weight of the tray system itself. And as you can see from this chart, the reduction is pretty dramatic.
So just let that sink in for a second. Making a deliberate choice in material can cut the tray's own weight by 35 to 40%. That has massive knock-on effects for, well, everything. The support structures you need, the safety of the installation, and of course, the total cost of the project.
All right, we've talked about those nice, clean, uniform loads you see in the spec sheets. But let's be honest, the real world is a lot messier. What happens when you have to mount a heavy piece of equipment right onto the tray? Let's see how the theory actually translates to practice.
Let's imagine a super common situation. An installer has a 60-kilogram junction box, and they need to mount it smack in the middle of a 3-meter span of cable tray.
So here is the big engineering puzzle. How does that one single concentrated weight affect the tray's overall load rating? You can't just pretend it's not there, right? It has to be accounted for.
And the answer is actually fascinating. That single 60-kilogram point load creates what we call an equivalent bending load of about 40 kilograms per meter across that whole span. This is so important. It means the tray has to be specified to handle the weight of all the cables plus this extra 40 kilograms per meter from that one junction box.
You know, a cable tray system can be incredibly strong, but it's only as strong as its weakest link. And that's why the connections, the joints between the individual sections, are one of the most critical parts of the entire setup.
Making a truly secure connection is a very precise process. It's not just about slapping two pieces of metal together and cranking on a bolt. You have to position the splice plates perfectly for mechanical strength, then apply the exact right amount of torque to the fasteners, and finally install a bonding jumper to make sure you have solid electrical grounding across that joint. And these specs are absolutely 100% non-negotiable. A torque of 20 to 25 Newton meters isn't just a suggestion. It is a hard engineering requirement to guarantee the mechanical strength of the whole run. And that bonding jumper, it's not optional. It's absolutely essential for safety and for the system to perform the way it was designed.
So let's just quickly recap the 4 key engineering pillars we've just walked through. First, that I-beam geometry is where the tray gets its built-in strength. Second, choosing the material is a critical calculation of weight versus strength.
Third, those pesky point loads have to be converted into their equivalent distributed load. And finally, number 4, the integrity of every single connection is what determines how the entire system performs.
Which really just leaves us with one final thought to chew on. When you look at a set of plans, yeah, the cable routing might be specified. But after digging into all these details, it really makes you ask the question, is it truly engineered?